All right. Going to be working now on the homework for 8.2. All right. We're going to start out with number 7. Number 7. The instructions here determine whether the geometric series, so they're telling us that this is geometric. That's nice. On a test, I normally won't tell you that. 10 minus 2 plus 0.4 minus 0.08 plus ... Determine whether or not that's convergent or divergent. If it's convergent, find its sum. So remember, for geometric series, we have actually two formulas. Sum n equals 1 to infinity of a r to the n minus 1 will be equal to a over 1 minus r if the absolute value of r is less than 1. We also have, you can change the index from 1 to 0, a r to the n, and this will be equal to the same thing. So all that did was shifted the index. That changed from n minus 1 to n. That changed from 1 to 0. So that this is our geometric series. If this absolute value of r is greater than or equal to 1, the series diverges. All right, so what we need to do is figure out if we can get this to be written in this form. I'm going to work with that top one. All right, so let me try and figure out what the terms of this series are. So 10 is 10, sure, 10, minus 2, plus, let's see, that's 4/10, minus, see, this is 8/100, and then I'm guessing my next one, let's see, what would it be? We have to figure that out, right? So maybe let's write this one as 2 over 1. And then let's rewrite this first one as 10 over 1. All right, this is going to be tricky. I've got to make some guesses here. Looks like the only pattern I see right now is we have an alternating series, right? So I'm going to try and write this out. My series looks like it's the sum n equals 1 to infinity. Since it alternates and starts with a positive, my series must include negative 1 to the n plus 1, because when I plug in 1, I need a 2 here, so that squares and gets a positive. Everything after that will switch back and forth. So that will create my alternating part. Fraction-wise, I think I see a pattern here. This looks like, 2, 4, 8, sorry, I almost said 6. 2, 4, 8, those look like powers of 2. So it looks like I've got 2 to the first power, 2 to the second power, 2 to the third power. Of course, I've got minus here, plus here. On the bottom, this looks like 10 to the first power, 10 squared, 10 to the first power, 10 squared. And I'm hoping this is going to work. If I do that, then this 1 down here has to be 10 to the 0, right? If we're going backwards. Yes, and that works. But then this first one, following this pattern, I would have to have a 2 to the 0 here, and on the bottom a 10 to the negative 1. So the question is this this? And in fact, it is. 2 to the 0 is 1. 10 to the negative 1 is 1/10. And when you flip that up, you get 10. So this, in fact, is my series. Now, of course, it continues forever. So looks like I've got powers of 2 starting at 0. To make that happen, 2 to the n minus 1. On the bottom, I have powers of 10 starting at negative 1. To make that happen, I've got to go 10 to the n minus 2. So let's just check it. If I plug in 1, I already know I'm going to get 2 here, and that's going to square. It's going to give me a positive. If that 1 goes in here, 1 minus 1 is 0. 2 to the 0 is that first one. And then if I plug in 1 here, 1 minus 2 is negative 1. I get 10 to the negative 1, and that's the first one. And then after that, the powers just keep going up by 1. Powers keep going up by 1. So I'm good to go. So this looks like it. But recall that what I need to do is I need to make it look like this. So I need to figure out, is there a constant out front, and is there a number that's being raised to a power? So let's work on this. Could you rewrite this like this? We already have an n minus 1 on the 2, which is good. But I have an n minus 2 here. I don't like that. I would rather it be an n minus 1. So I'm going to make it happen. I've got negative 1 to the n plus 1 times 2 to the n minus 1 over 10 to the n, to the n minus 1 plus 1 minus 2. So just, again, what we're doing is we did this a while back. We're realizing a hidden 0 in here, but we're rewriting that 0 as minus 1 plus 1. And that way, we get the n minus 1 that we need right there. So now, I can rewrite this as sum n equals 1 to infinity, negative 1 to the n plus 1, times 2 to the n minus 1 over, now I'm going to split it right here. I've got 10 to the n minus 1 times, and then now use this is 1 minus 2 is negative 1, 10 to the negative 1. Let's just check it. If we were to put these two back together, you would add these two together. N minus 1 plus negative 1 is the same as minus 1. So this would be n minus 1 minus 1, that's n minus 2, which is the original problem. But notice now I've got both of these to the n minus 1. So all I need to take care of, because this is just a number, right? There's no n on it, is to figure out how I can rewrite this as n minus 1. And I can do the exact same thing that I just did. So I'll do this. I'll rewrite this as sum n equals 1 to infinity, negative 1 to the n minus 1 plus 1. That's my hidden 0, but I already had a plus 1. And then I had my 2 to the n minus 1 over 10 to the n minus 1 times 10 to the negative 1. And this becomes sum n equals 1 to infinity. All right, rewriting that, that's negative 1 to the n minus 1 times, so I'm splitting it here, negative 1 to the 1 plus 1 is 2, negative 1 squared, times 2 to the n minus 1 over 10 to the n minus 1 times 10 to the negative 1. All right, remember I'm trying to get to this. Negative 1 squared is 1, so I don't even need that there. And so now what I'll do is I'm going to take everything that has an n minus 1 in it as a power and put those together. So I'm taking negative 1 to the n minus 1 times the 2 to the n minus 1 over 10 to the n minus 1. Since these are all to the n minus 1, I can write this as sum n equals 1 to infinity. All of this to the n minus 1. So negative 1 times 2 over 10. Negative 1 times 2 over 10, all of that to the n minus 1, which is going to be negative 2 over 10, which is negative 1/5. Negative 1/5 to the n minus 1. And then, so I've taken care of this, this, and this. I still had a 10 to the negative 1, which I can move up as a 10. So I have a 10 sitting here on top, which I'll write like that. And that's it. We've got the form we need. We have that a in the problem is 10. We've got that r is negative 1/5. And we've got the n minus 1 to match up, right? Sum is going from 1 to infinity, and so we can determine what this does. So let's now check to see what we need for convergence. To converge, we need to take the absolute value of r. We need that to be less than 1. That's the question. Well, the absolute value of r is the absolute value of negative 1/5. Is that less than 1? Well, absolutely. That's 1/5 is less than 1. Check. So it converges. All right? So this series converges. And what does it converge to? It converges to a over 1 minus r, which is going to be for us 10, that's a, over 1 minus r, which is negative 1/5. So this is going to be 10 over 1 plus a fifth. Putting the denominator together into one fraction, this is going to be 6/5. So 10 over 6/5, which is the same as 10 times 5/6, which is 50 over 6. 2 goes into each of those, 25/3. So that series is converging. If you were to add those up using that same pattern forever, it would get closer and closer and closer and closer to 25/3. All right, give me just a second here. All right, let's look at, I'll let you try 8 on your own because 8 is very similar to that. Let me look at 9. So in that problem, there was a lot going on in that problem. We had to find the pattern. We had to, once we established the pattern, rewrite it. Number 9 is a little more straightforward because they actually give you the summation. They give you n equals 1 to infinity. And they give you negative 3 to the n minus 1 over 4 to the n. So they've already done a lot of the groundwork for you. They've already determined the formula. And so it's now up to you to see if this is geometric, which you know because they told you it's geometric. You just have to figure out if it converges. So what you need to do is make sure that anything that's raised to the n power, that's an n minus 1, which right now this one on the bottom is not. So I'm going to rewrite this. I'm going to use that hidden 0 again. I'm going to rewrite this as negative 3 to the n minus 1 over 4 to the n, and here we come, minus 1 plus 1. And see, there wasn't anything out here, so I don't need to put anything else. And I'm going to split it right here. So this is sum n equals 1 to infinity of negative 3 to the n minus 1 over 4 to the n minus 1 times 4 to the 1. So if you put these two together, you get back this, which is the same as this. So I don't need the 1 here. I'll get rid of it. And now I can rewrite this, sum n equals 1 to infinity. Now the things that are raised to the n minus 1 are these two. So I'm going to put them together. Negative 3 over 4 to the n minus 1. And then I have a 4 over here on the bottom, so I'm going to put a 1/4 out front. I'm going to make sure it's coming out on camera. Yes. So we can identify now that we have an a, it's a constant, and we have our r is the thing that's being raised to the n minus 1. I need to check to see that the absolute value of r is less than 1, which it is. So the absolute value of r less than 1, that's the question. Absolute value of r is absolute value of negative 3/4. It's less than 1, check. And therefore this converges. So therefore we get convergence. And what does it converge to? A over 1 minus r, which is going to be a, 1/4, over 1 minus r, which is negative 3/4, which is 1/4 over 1 plus 3/4, which is 1/4 over, let's see, 7/4. And if you flip, this is 1/4 times 4/7, and you get 1/7. Okay, good. Let's see, that was number 9. Number 10, work yourself, but I'll give you a hint. Number 10, it diverges because the absolute value of R in that problem turns out to be negative 10/9, and the absolute value of that is greater than 1. Number 11, let me work that one for you. Pi to the n over 3 to the n plus 1, n starts at 0. Okay, so sum n equals 0 to infinity, pi to the n over 3 to the n plus 1. Okay, so notice that this starts at 0. If that starts at 0, then our formula that we need to make it look like is this. So we need to the n power instead of the n minus 1 power. All right, so I'm going to stick with this, and I'm actually going to try and make both of these to the n. So if I need to make this to the n, I need to subtract 1 from that. So I'm going to subtract 1 and add 1, right? So check this out. Or you know what? That's too much work. Let's do it this way. It's a lot easier to do it this way. Pi to the n, and then just rewrite that as 3 to the n times 3 to the 1. So if you put those two together, you get this, but peeling them apart, you can see you've got this here. They're both to the n power. So what I'll do now is I'll rewrite this, sum n equals 0 to infinity. Now I have pi over 3 to the n, that's those two, and then here I had a 1 over 3, so my a is 1/3. So a is 1/3, r is pi over 3. So now we need to check for the convergence. What I want is the absolute value of r to be less than 1. Well, the absolute value of r is the absolute value of pi over 3. Is that less than 1? Question? No, it is not. Pi is 3.14, and some change after that, over 3, that's a number that's bigger than 1. This doesn't work. Therefore, this geometric series diverges. Number 10 works the same way. That's what I was getting at. Number 12, I'll just give you a hint, it does converge, but your r is weird in that problem, just kind of strange, it has a radical in it. Number 13. All right, so number 13, they're not telling you it's a geometric series. This is where we start. For the first time, we have a series, and we're not being told what it is. We just have to figure out if it converges or diverges. So we can use anything we've learned in this section to determine this. So 3 to the n over e to the n minus 1. So when I'm looking at this series, I'm noticing that my summation, my index n here, starts at 1. So if it is geometric series, I would be using a certain formula, right? If it's geometric, I would be using that one. I also noticed that my numerator and denominator, they both have bases that are numbers, right? There is a number, e is a number. And more than that, they're both raised to an exponent with n in it. And that's exactly what a geometric series looks like. So if I can make these both be n minus 1s, I should be able to use that formula. So I'm going to rewrite this, sum n equals 1 to infinity. I'm going to go 3 to the n minus 1 times 3 to the 1. So I've done that a few times now. I'm hoping you're okay with that, right? My hidden 1, my hidden 0, minus 1 plus 1. And then I've got these two are both to the n minus 1. So I get n equals 1 to infinity. This is my number that's by itself, 3, and then times 3 over e to the n minus 1. So there's my a, there's my r. But the absolute value of r needs to be less than 1, and the absolute value of r is 3 over e. Is that less than 1? No. E is 2.718 something. So when you try that, it's going to diverge. So this diverges. But it was a geometric series, all right? It was geometric. Let me see about 14. Let's see, I think I'm going to need to do the evens here. 14. Sum k equals 1 to infinity. Of k times k plus 2 over k plus 3 squared. All right, so we have an important test that we use whenever we're looking at series. I mean, right now I look at this and I'm not thinking geometric at all. And the reason is because I don't have numbers raised to the n, or in this case we're using the index k. So I would need something like sum k equals 1 to infinity a r to the k minus 1. I would need some base raised to these powers. None of these k's are powers, so geometric is off the table. All right, not even thinking about it. But we do have a test. It's called the nth term test. It's the first test we usually want to run. Nth term test. And what it says is that if you look at the sequence of numbers that's generated in this series, right? K being 1, then K being 2, then K being 3. That's just going to create a list of numbers that we're adding up. If we take the limit as, in this case, we usually use n here, but since this problem is using k, what we're going to do is let k go to infinity of the sequence. If this limit, so if the a sub n, which is the part inside, right, that's the a sub n, the thing we're adding up, if that a sub n goes to some place, right, other than 0, so if it does not go to 0, then the series diverges. So that's such a powerful little test. It's saying that, look, I can guarantee you that if these numbers in here, as you plug in 1 and 2, if those numbers that you're listing out, if they don't go to 0, there's no way this thing can converge. All right? If they go to 0, you actually don't know. It could converge, it could diverge. And I showed you examples of that in class. So I like this test right now because it's always the first thing you want to kind of try. And I also see that if I just expand out the numerator and denominator, I'm going to get k squared plus 2k over k squared plus 6k plus 9. And this looks like infinity over infinity, and I can use L'Hopital. And if I do that, and you know we've done this in the previous section, if I do this, I'm going to determine that this is going to go to 1. And since that goes to 1, that is not 0, right? It's going to somewhere other than 0. I can conclude that this diverges. All right? Just remember though, if this went to 0, your conclusion would not be that it converges. It would just be that you don't know. But if it goes somewhere other than 0, you can guarantee, say, diverges. So that's it. How about number 15? All right, I think 15 is going to be pretty much the same thing. Sum n equals 1 to infinity of n minus 1 over 3n minus 1. So this is the exact same thing. We look at this, it's not geometric. So I try the nth term test. Here I'll use n instead of k. I'll take this, and then I'll do L'Hopital's rule on it right here. And when you do that, you should get 1/3. And that's not 0. So it diverges. All right, how about number 16? Sum n equals 1 to infinity of 1 plus 3 to the n over 2 to the n. Well, should we try the nth term test again? Maybe we'll get lucky. What does 1 plus 3 to the n over 2 to the n go to as n goes to infinity? That would be infinity over infinity, so you would use L'Hopital, right? You could use L'Hopital. Yeah, you know what? Let me do this because I want you to see what happens. If I do limit n goes to infinity here, after I do L'Hopital, and I'm keeping everything in n, I'm not going to switch to x and back because I'm hoping you've done enough of these to realize that you're just going to, that's more of just to understand that, look, you know, technically you can't take the derivative of a sequence, but since we've done it enough, we'll just say once you do L'Hopital's rule and switch back, the derivative at top would be something like 3n natural log 3, 3 to the n natural log 3, the bottom would be 2 to the n natural log 2. And now this right here can be rewritten. So we have limit as n goes to infinity of 3 over 2 to the n times natural log 3 over natural log 2. And as n goes to infinity now, this number is bigger than 1. This thing is going to blow up. It's going to get huge. This is just a constant. So this is not going to 0. And so it diverges. Now another thing you could do, so this diverges, we're done. But another thing you could do is you could have split this into 2 fractions. And then what you could have done is you could realize that these are both geometric series. So this sum, n equals 1 to infinity. This one right here is the same as 1 over 2 to the n. And then plus this one over here is 3 over 2 to the n. And so, of course, you have to get these to look like n minus 1s. You don't need it to draw your conclusion right now because you already kind of know what's going to happen, but I'll show it to you anyway. This would be 1/2 to the n minus 1 times 1/2 to the 1. That's realizing the hidden 0. And then plus 3/2 to the n minus 1 times 3/2 to the 1. And so you know that if you split this up into 2 sums, this is a geometric series. This is A, this is R. The absolute value of R is less than 1. And so this piece would converge. But this one, here's your A, here's your R. This R, the absolute value of that R is not less than 1 because it's 1/2. So this would diverge, this would blow up. And if this one blows up, the whole thing's going to blow up. So you're basically going to come up with the same conclusion that it diverges. Just that's one way using the nth term test, and the other way is just to look at it as a geometric series. Or actually, the sum of 2 geometric series. Hope that made sense. So these first couple of problems is showing the power of the nth term test. Let's see. All right, 18. Oh, wait. Okay, 17. I'll give you a hint on 17. I'm not going to work it. I'm just going to let it get set up for you. Sum, it's very similar to the last one. 1 plus 2 to the n over 3 to the n. So what they did is they switched. Instead of 3 to the n over 2 to the n, they went 2 to the n over 3 to the n. So if you try the nth term test, you're actually going to get 0. I'm going to show you because I want you to see that it fails. So I do 1 plus 2 to the n over 3 to the n. I do my L'Hopital rule on this. And the top, the derivative is 2 to the n, natural log 2, over the bottom is 3 to the n, natural log 3. And then this right here is 2/3 to the n. And as n goes to infinity, since this number is between 0 and 1, this thing goes down to 0. Who cares what that is? That's a constant. So this thing does go to 0. So the n-term test tells you that if this thing does not go to 0, it diverges. Since it goes to 0, the test is inconclusive. I don't know how much I can stress that to you. It tells you that you're going to have to find some other way of figuring out if it converges or diverges. So we go back now. And like I said, I'm not going to work through this whole thing. But if you split this up into 2 again, then you can rewrite this one as 1/3 to the n plus, and then this one 2/3 to the n. And then since it starts at 1, make this an n minus 1 by seeing the hidden 0, the hidden 0. Working them both out separately, you're going to get an a and an r for this one, an a and an r for this one. Both the absolute value of the r's are going to be less than 1, which means they're both going to converge. You're going to use the formula a over 1 minus r to get that answer, the formula a over 1 minus r to get that answer. Add the two answers together, that's your sum. So this one will converge, but I'm not going to show the work. All right, now 18. Sum n equals 1 to infinity, cosine 1 over n. Let me try the nth term real quick. So I'm going to take the limit as n goes to infinity of cosine of 1 over n. Okay, 1 over n as n goes to infinity goes to 0. Cosine of 0 is 1, and that is not 0. Therefore, this diverges. So that's a simple one again with the nth term. It's very useful, that test, huh? All right, how about 19? Sum n equals 1 to infinity of the nth root of 2? What? Nth root of 2? All right, we haven't seen this before. Let's just make sure we understand what the nth root of 2 means. This means 2 raised to the 1 over n. That's what the nth root means. Just like if you were to have the square root of 2, that'd be 2 to the 1/2. Or if you had the cube root of 2, that'd be 2 to the 1/3. Same thing. The nth root would be 2 to the 1 over n. Huh. All right. Well, let me try the nth term. Nth term test. So what's the limit as n goes to infinity of 2 to the 1 over n? And I'm hoping that this is going to go to something other than 0. And it's nice because n goes to infinity, 1 over infinity, that's 0. 2 to the 0 goes to 1, and that's not 0, and therefore this diverges. And these are all working out very nice. When are they going to get hard? Number 20. Diverges. Sum n equals 1 to infinity. And then we have 0.8 to the n minus 1, and then minus 0.3 to the n. There we go. Look at where the n is. The n's up in the exponent. The bases are just numbers. That's looking like geometric series. In fact, this one looks exactly like a geometric series. This one is sum n equals 1 to infinity of 0.8 to the n minus 1. Here, the a in front is a 1, and then the r here is the 0.8, which is definitely less than 1, so that's going to converge. Minus, now I have another sum, so I'm splitting this up into two sums, n equals 1 to infinity. This one is to the n, so I need it to be n minus 1. So how about 0.03 the n minus 1 times 0.3, like that. So again, peeling off 1 using the hidden 0. So this time, this is my a, and this is my r. and this r, the absolute value of it is less than 1. So we're going to get two convergent geometric series here. And so the sum of this one, remember the a is a 1 right here, is 1 over 1 minus 0.8. And then minus, right, this one is a, which is 0.3 over 1 minus 0.3. So let's try and figure out what this is. This is equal to 1 over 0.2 minus 0.3 over 0.7. And I know you want to get your calculator out right now, but 1 over, this is 2/10 minus 3/10 over 7/10. I'll flip this one up like this. This will become 3/7. Over here, I'll flip that up, that's 5. And so we get common denominator here, 7, 7, get 35. Minus here's 32/7. What was that? I have a reminder here for something. Oh, you got to be kidding me. Why? What? That's not right. What am I doing here? What number was that? Number 20, okay. All right, number 21, I'll let you do on your own. 21 is very much like 18. It's going to diverge, but you need to convince yourself. Something about arctangent, when you do the n-term test on that, what happens is n goes to infinity. It's like arctangent of infinity. What is that? I hope you know by now. All right, 22 is interesting because it looks like, what the heck? Sum k equals 1 to infinity. Cosine of 1, all of that to the k. What? What the world? Well, this is actually a geometric series. We have the index k is up here in the exponent. And so, I mean, that's basically like almost like the r to the n. So we'd like that to be n minus 1, but let's figure out on a calculator what cosine of 1 is. Because what does that need to be? It needs to be less than 0, right? So we make sure that we are in radian mode on our calculator. And we do cosine of 1. So let me just figure that out. Cosine of 1 is approximately equal to, let's see, I'm in radians, 0.54. Good enough. But that definitely means that that would be less than 1. So I know it'll converge. So I need to make this a minus 1. So this is where I do minus 1 plus 1. So minus 1 plus 1, I think, hopefully I've done this enough. But that's what happens. Right, if I rewrite it. So my a here is this, and my r here is this. And I already know that the absolute value of r is less than 1. So this will converge, and what it converges to is a cosine 1 over 1 minus r, 1 minus cosine 1. And let me see if they want you to write that down a certain way. Yeah, no, that's it. You could get a decimal approximation to that if you want, but that's the exact answer right there. This converges to this. Kind of weird, huh? 23. Here we go. 1/3 plus 1/6 plus 1/9 plus 1/12 plus 1/15 plus ... See if we can come up with a formula for this. Sum n equals 1 to infinity. So these are all just multiples of 3. This is 3 times 1, 3 times 2, 3 times 3, 3 times 4, 3 times 5. So it looks like 1 over 3n will work. And this is not geometric because this n is not in the power. And so what I might need to do here is take a look at the nth term test. It's been saving us so far. And so what I do is just take the limit as n goes to infinity of the sequence, which is 1 over 3n, but that goes to 0. And that's bad. That means that this test fails. All right? It's inconclusive. I don't know what the answer is. What I do know is that if that went to something other than 0, it would diverge. But since it goes to 0, I don't know anything. So this is where you have to go back and look at the lecture and realize that what you have here is a constant on top. Okay, so you've got your sum. You've got some constant on top, which in this case is the 1, over some linear expression. Okay, the linear expression in the variable n, which is our index. Anytime we see this, this is the same as a harmonic series. So what we could do is essentially take that 3 out, make it a 1/3, and that's your harmonic series right there. And so we know that all harmonic series diverge. So your answer is diverges. There's no work that needs to be done other than to identify it as a harmonic series. All right, 24 is going to be the last one on this video, and then I'm going to take a quick break. 1/3, 2/9. Okay, 1/3 plus 2/9 plus 1/27 plus 2 over 81 plus 1 over 243 plus 2 over 729. All right, so we look at this and we try and figure out if we can get a pattern to this. And it looks like the bottoms are all powers of 3. It looks like 3 to the first power, 3 squared, 3 cubed, 3 to the fourth, 3 to the fifth, 3 to the sixth. But the issue that I have is how am I going to make the top switch back and forth between 1 and 2? That's going to be really, really difficult for me to do. So what I'm going to do instead is I'm going to look at this as 2 series. Here's one of them, and here's the other. Okay? The one that has the 1s on it, let me write that one first. It's 1/3 plus 1/27 plus 1 over 243 plus ... And then I have the other series in there, which is 2/9 plus 2 over 81 plus 2 over 729. Now what I'll do is I'll realize, I'm going to do like, I'm going to work at this, and I'm going to figure out what's the sum for this one and what's the sum for that one. So the sum for this one, realizing we've got 1 over 3 to the first plus 1 over 3 cubed plus 1 over 3 to the fifth, right? Plus ... And then this is 2 over 3 squared plus 2 over 3 to the fourth plus 2 over 3 to the sixth. So these are all 1 over 3 to a power, but these powers are odd. This is 2 over 3 to a power, but these powers are even. So I can rewrite this as sum n equals 1 to infinity of 1 over, because it's always 1 on top, and then 3 to the, how do we say odds, starting with 1, 2n minus 1. Plus this one, which is going to be 2 over, n equals 1 to infinity of 3 to the, how do we do evens starting at 2? 2n, like that. All right, that should create these two, and then those two added together creates the original sequence, or series. It's kind of clever, huh? Now let's look at these. These look like geometric series because what we have is our base to a power. We need these powers to be n minus 1s because we're starting at n equals 1. So watch what I do first. Tell me if you agree with this. That's the same, because if I take 1 and raise it to this power, I just get 1. Any power, doesn't matter. And then this, 3, I get that. Then I have plus over here. I'm going to do the exact same thing. Actually, I think what I'll do, yeah, I'll do it. N equals 1 to infinity. I got that 2 right here. And then I'm going to rewrite this as 1/3 to the 2n. Notice I cannot put 2 over 3 to the 2n because this 2 never changes. If you put it in here, it's going to start getting raised to powers. So that should be both of those. And now I need to force these to be n minus 1s. Not 2n minus 1s, n minus 1s. So how in the world are we going to do that? How are we going to do that? How do you force that to be a 2, or sorry, the 2n minus 1, how do I force it to be just an n minus 1? Well, see if you agree with this. N minus 1 to the infinity, or sum n equals 1 to the infinity. How about this? 1/3 to the 2 to the n minus a half. Ooh, what the hell happened there? Well, remember, if you have something to a power, you multiply these two powers. And if I multiply 2 to this, I get 2n and then minus 1. So I could do that. That would be okay. Over here, I can do the same exact thing. You'll see where this is going. I did these in class too. So 2 times, here this one is a little easier. It's 1/3 to the n, to the 2 to the n. So if I multiply this times this, I get this. So let's go a little bit further. This is sum n equals 1 to infinity. Now 1/3 squared is 1/9. So this is really 1/9, right, to the n minus a half. And then plus sum n equals 1 to infinity. I've got 2 times 1/3 squared is going to be 1/9 to the n. Now what I need, see, I've kind of gotten rid of that 2 that was causing a problem because I needed it to be an n minus 1. Now I just have n's. I need to make this an n minus 1. I need to make this an n minus 1. So here's where I come in with my hidden 0. So I'm going to subtract and add 1 in there. So this becomes sum, let me get rid of this. This becomes sum n equals 1, 1/9. And then I'm subtracting and adding 1. So n minus 1 plus 1 minus a half. And I'm going to split it right there. Then on this one, I've got my 2. This is a 1/9. And then on my power n, minus 1 plus 1, and I'm going to split it right there. So what we get is this, equals sum n equals 1 to infinity. I have 1/9 to the n minus 1 times 1/9 to the 1 minus a half is a half, plus sum n equals 1 to infinity of 2 times 1/9 to the n minus 1 times just 1/9 here to the first power because of that. I'm so close. On this one, I have my r raised to the n minus 1. Here's my a, this whole thing. And what is that? What is 1/9 to the 1/2? Well, that's just the square root of 1/9, which is 1/3. So that a is 1/3. Over here, I need to do a little bit. This is 1/9, but I had a 2 out there. So how about we take that 2 and we put it right here, 2/9, get rid of this. And this is my a and this is my r. On both of these, the r is less than 1. The r is less than 1, so these will both converge. So remembering, I'm going to have to erase that. This will now be equal to A over 1 minus R. So it was 1/3 was A over 1 minus R. Plus, over here, A is 2/9 over 1 minus R. So this equals 1/3 over, let's see here, that's, can't do simple math right now, 8/9, and then plus 2/9 over 8/9. And we can flip here. When we flip that up, we get 2 over 8, that's 1/4. Plus over here, when we flip, let me just flip it, 9, 8, we get what, 3, that cancels, we get 3/8. And when we put those two together, we should get 5/8. 5/8. There we go. Okay, I think that that's sufficient for now. I am going to need to do a couple of more, but that should get you going, I think. Okay, I'm going to be continuing here the 8.2 homework. I'm going to be doing 25 through 28, then I'm going to be doing like 31 through 30, maybe 34. So 25. Sum n equals 2 to infinity of 2 over n squared minus 1. All right, so we take a look at this. It's not geometric because I don't have a number to the power n. If I try my nth term test on this, okay, so let me try the nth term. Limit n goes to infinity of 2 over n squared minus 1. This goes to 0, so this test fails. And so I've got to figure out something else. All right, well, let me try something else here. I could possibly look at maybe it's harmonic, so it diverges, but see the denominator is not linear. So we have a constant on top, but we have a quadratic on the bottom, so that it's not harmonic, so we can't just conclude it diverges. So maybe we can factor out that denominator. How about that? And that'll give me n plus 1 times n minus 1. Now, I cannot split this up into two different series, you know, one like with 2 over this and 2 over that, because you can't work with fractions that way. Each one of these by themselves are linear, but multiplied together is quadratic. So we're still not going to get harmonic that way. But what we do is we go back and we realize, oh, wait a minute, we could do a partial fraction decomposition on that. I can try and rewrite 2 over n plus 1 times n minus 1 as, I have two distinct linear factors, so a over n plus 1 over b over n minus 1. And then going through, so we did this when we were doing integration with partial fractions. We go ahead and try and determine what a and b are. And let's see, if n is 1, then it kills off this, and we get 2 equals b times 1 plus 1 is 2, so 2b, so b is 1. So know what b is. If n is negative 1, it kills off this one, and I get 2 is equal to negative 2a, so a is negative 1. Negative 1. All right, so that means I can rewrite this series as series n equals 2 to infinity of, let's see, negative 1 over n plus 1, and then over here plus 1 over n minus 1, like that. You know, I'll just leave it like this. Okay, so at this point you might think, okay, well, sure, this is going to diverge because this is harmonic and that diverges, and this is harmonic and that diverges. However, This one diverges, but it's negative. So it's going to like negative infinity. This one's going to positive infinity. So what you're getting is something like negative infinity plus infinity when you break this up into two sums. And that we've never been able to determine. Now, if one of them goes to negative infinity and the other one goes to a number, of course, that's going to diverge. Or the other way around. If this went to a number and this went to infinity, that would diverge. But the fact that they're both going to infinity and one of them is negative and one of them is positive, we cannot figure out what that is. So we've got more work to do here. I just got a text, so let me just check what this is. Okay. All right, so let me try and write out the first few terms of the sequence. And you know what I'll do, since this is my first one, I'm going to write out the first few terms using this first. If I let n be 2, I get 2 over, see 2 squared is 4 minus 1 is 3. If I let n be 3, I get 2 over, let's see, 3 squared is 9 minus 1 is 8. And then the next one, 2 over, let's see, n is 4 now, so 4 squared, 16 minus 1 is 15. And then 2 over, let's see, n is 2, 3, 4, 5, 25 minus 24. And so, I mean, oh, sorry, doing the sequence. I took a break and I've lost my train of thought here. So this is what we've got there. I don't really see anything happening that is going to help me figure out what's going on. But if I rewrite it this way, watch what happens. So if I let n be 2, I get, and I think what I'll do is I'll write this over here. If I let n be 2, I get negative 1 over, let's see, 2 plus 1 is 3, plus, let's see, I'm let n be 2, so 1 over 2 minus 1 is 1. Plus, now I let n be 3, so I get negative 1 over 3 plus 1 is 4, plus 1 over, let's see, 3 minus 1 is 2. And then plus the next one, negative 1 over 5. And then I get plus 1/3. And then plus negative 1 over 6 plus 1/4. And that's what keeps happening. So I look at this and I notice something. I notice that this negative 1/3 would actually cancel out with that positive 1/3. Those two would actually go away. And then the negative 1/4 would cancel out with this positive 1/4. And the negative 1/5 would probably cancel out with the 1/5 I would get down there. And the negative 1/6 would cancel with something I would get down there. So I'm noticing this is going to be a collapsing series. Now, they tell you that inside, in the instructions, they tell you it's a telescopic series, which is also called a collapsing series. They give you that information, but you should be able to notice it yourself. So look at this series, say, it factors, and do your partial fractions. So the proper technique, once we understand that it's a collapsing series, the proper technique is to do the following. You first find S sub n, which is the nth partial sum. Once you find out what that is, then you let n go to infinity. Or in other words, you find the limit as n goes to infinity of that nth partial sum. So we got kind of two steps here, all right? So let's do the first step. Let's find S sub n. I'm going to need some space for this, so I'm going to write it out like this. S sub n is the sum that I get here when I start at 2, right, and I stop at some n here, capital N, let's say, and that's what this is, like a capital N. Okay, so I'm going to start at n equals 2 and stop at some capital N. So what do we get when we do this? Well, we already did the first one. It was negative 1 over 3 plus 1, and then it was negative 1 over 4 plus a half, and then it was, I forgot the plus sign between those. Negative 1 over 4 plus 1/2, and then it was negative 1 over 5 plus a third, and then negative 1 over 6 plus a fourth, and plus dot, 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 dot. And now what we'll do is we'll write out the last ones, and I'm going to start over here. The last one would be what I get when I plug in capital N, which is 1 over capital N plus 1 over capital N minus 1. So that's what happens when I plug in N. The one before it is what I get when I plug in N minus 1. So plug N minus 1 into this, you get negative 1 over N minus 1 plus 1 is just N, plus over here 1 over N minus 1 is N minus 2. And we'll look at the one in front of that. This is what I get when I plug in N minus 2. So if I plug in N minus 2 here, I get negative 1 over N minus 2 plus 1 is N minus 1. Plus, if I plug in N minus 2 here, I get 1 over N minus 3. And I'm hoping that's enough for me to establish the pattern of what's going on here. So notice that the first number in the first parenthesis is going to be killed off by the second number 2 parentheses away. So let's see, the first number in a parentheses should be killed off by the second number 2 parentheses away. Yes. The first number should be killed off by the second number in the parenthesis 2 away. So it would be 1, 2, it would be in here somewhere, and that negative 1/5 would go away. This 1/6, negative 1/6, would get killed off by something in here. It would go away. Now, on the other hand, you can look at it backwards. The second number in a parentheses gets killed off by the first number 2 in front of it. So the second number in a parentheses gets killed off by the first number 2 in front of it, and so on and so forth. So look at this second number. For it to get killed off, we need to have something in a parentheses 2 in front, which we don't have. So this number stays. Nothing touches that one. This is the second number. I need to be able to go 2 in front, which, again, I can't. So that stays. This second number, yes, it did get killed off by that one. And now I come over here, I do the same thing. The first number should get killed off by something second number 2 away, which is here. Right? This first number, I cannot go out because I stop here at N. So there's nothing that kills that, it stays. This first number, I need to go this way. I can't go anymore, so this stays. This second number gets killed off by 2 in front, the first number, so it's somewhere in there, that gets killed off. The second number here gets killed off by something 2 in front, the first number in a parentheses, 2 parentheses away, so something in there kills off that one. So the only thing left at the end of all of this, okay, this is where we get the collapsing from. Everything pretty much on the inside here cancels out. And the only thing left for S sub n is a 1 plus a half, which is 3 halves, plus over here a negative 1 over n, and then another 1 plus a negative 1 over n plus 1. That's S sub n. And now what we do is we take the limit as n goes to infinity of this, 3 over 2 plus negative 1 over n plus negative 1 over n plus 1. And that is, what, that goes to 0, that goes to 0, so I just get 3 halves. So this telescopic or collapsing series converges to 3 halves. Okay, that was number 25. Let's look at 26. Natural log of n over n plus 1. Natural log of n over n plus 1. Sum 1 to infinity. Natural log of n over n plus 1. Now they tell you again that this is a collapsing series, but let's act like we didn't know that. So I would probably start this with the nth term test. I would take the limit as n goes to infinity of natural log of n over n plus 1. The inside is infinity over infinity, and when you do L'Hopital on that, you're going to show that goes to 1. Natural log of 1 is 0, so this thing goes to 0, which means this test fails, right? So then you look at that, and I don't know, maybe you try starting to plug some numbers in. If you let n be 1, you get natural log of 1/2, plus now you let n be 2, natural log of 2/3, plus natural log of 3/4, and there's really nothing canceling out. It's all addition. So in order for it to collapse, we have to turn it into subtraction. So what we notice is that we can use the property of logs and split this into 2 logs, right? So if we have division inside of a log, it can turn into subtraction between 2 logs. And now when I write out the series, let's see what I get. If n is 1, I get natural log of 1 minus natural log of 2 plus natural log of 2 minus natural log of 3 plus natural log of 3 minus natural log of 4 plus, and then I keep going with this. And now I see some canceling. This is going to cancel with this is going to cancel with this is going to cancel with the next one, and so on and so forth. So that's actually going to be a nice collapsing series. So to do it correct, once I've identified that it does collapse, I'm going to write out what S sub n is. So that means I'm going to write this sum out, but I'm going to stop, okay? So natural log of 1 minus natural log of 2 plus natural log of 2 minus natural log of 3 plus natural log of 3 minus natural log of 4 plus dot, dot, dot. And then let me stop at n. That'd be natural log of n minus natural log of n plus 1. That's what I get when I plug in n. The one before this would be natural log, let's see, I'm plugging in n minus 1. So natural log of n minus 1 plus natural log of n. So when I plug n minus 1 right here, I get n. N minus 1 right here, I get n minus 1. And then I could do another one in front, but this is enough for me to see the pattern of what happens. You've got the minus natural log of 2 canceling here, minus natural log of 3 canceling here, minus natural log of 4 does cancel with something there. This one gets canceled by the one in front. So look, the ones that are right next to each other are going away. So the one right in front of this would cancel. This one should cancel with this. This one doesn't have anything over here. There's nothing over here for it to cancel with, so it stays. Natural log of 1 has nothing to cancel it because there's nothing in front of it. So our nth partial sum is natural log of 1 minus natural log of n plus 1. And natural log of 1 is 0. So this is just negative natural log of n plus 1. And so what happens here? We now say, all right, we found out what S sub n is. That's it right there. Let's take the limit as n goes to infinity of that nth partial sum. And if you let n go to infinity, natural log of infinity becomes infinite. So this heads to negative infinity. And that means this diverges. It's got to go to a number to say it converges. All right, number 27. N equals 1 to infinity. Three over n times n plus 3. Ooh, this one's going to be nasty. Okay, so I'll save us some time. The nth term test is inconclusive. It's going to fail because when you take the limit of the inside, it goes to 0. If you write out the first few pieces, nothing's going to cancel. So you go through and you do your partial fractions.
You do 3 over n times n plus 3 equals a over n plus b over n plus 3. And let me save us some time here. What is it? 1. Comes out to 1 and negative 1. So a is, when you do your partial fractions, a is going to be 1 and b is going to be negative 1. So this new series becomes sum n equals 1 to infinity of 1 over n minus, I'll just put the minus here instead of a plus, b over n plus 3. And I know I'm going to get some collapsing to happen here. So right now I'm going to start out with the nth partial sum. All right, so when I do the nth partial sum, I'm going to start plugging in numbers right here. When I plug in 1, I get 1 minus, let's see, 1/4 plus, let's see, 1/2 minus 1/5 plus 1/3 minus 1/6 plus 1/4 minus 1/7 plus 1/5 minus 1/8 plus 1/6 minus 1/9 and 1/7 minus 1/10 plus, and I have to stop this, but see I'm out of room over here. But I needed that many to see this cancellation. See, the cancellation occurs, let's see, this 1 doesn't cancel anything. This negative 1/4 cancels way down here. So the the second number in the parentheses cancels with the first number in the parentheses, 1, 2, 3 parentheses down the series. So second numbers cancel with first, 3 down to the right. So the second number here, oh yeah, these are gone, should cancel with the first number 3 down. So if I go 1, 2, 3, first number, there it is. So you can see this one and this one cancel, right? This second number here should cancel downstream. So I'll keep doing that, but I need to write the end of this, and I was out of room. So I'm going to do it like this. I'm going to start here. The last piece of my nth partial sum will be that with n plugged in, which is just itself. The one right before it is what I get when I plug in n minus 1. This is what I get when I plug in n. So when I plug in n minus 1 right here, I get 1 over n minus 1 plus 1 over n plus 2. So plug n minus 1 right there. N minus 1 plus 3 is n minus 2, or plus 2. The one in front of this is 1 over n minus 2 plus 1 over n plus 1. I'm going to do one more in front of that. 1 over n minus 3 plus 1 over n. And then in front of it, dot, 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 is this right here. So now getting back to this cancellation. We said the second one cancels with the first one 3 down. So that second one, this second one should cancel with the first one 3 down. 1, 2, 3, there it is. Gone, gone. This second one should cancel with the first one 2, 3 down. It does. So this second one should also cancel with something down here. All right? This second one should cancel with something down here. It does. This second one should cancel with something in here. It does. It's gone. Now, reverse that. Okay, reverse this so that when we come from the other end, we do it the opposite way. Second ones cancel with first ones 3 down. That means first ones cancel with second ones 3 ahead. So first ones, here this first one, should cancel with something 3 down over here, which is in here somewhere. That should go away. First ones should cancel with something 3 down, and here it should go away. First ones should cancel with something 3 down, should go away. This one you can see it. First ones should cancel with 3 down, second ones gone. So all the first ones are gone. Now, how about the second ones? In order for the second ones to cancel, right, just like this one, we need to be able to look 3 down this way. So this one, can we look 3 down? Nope, can't do that, so it stays. This one, we can't look 3 down, we have to stop, so here. And this one here stays also, because there's nothing down here. So our nth partial sum is everything that's left, and I'll kind of highlight that. It's this, it's this, it's this, it's this, it's this, it's this. Okay? These first ones needed something down here to cancel. There was nothing down there. So it's establishing a pattern. It's somewhat complicated, I guess, the first few times you do this. So now what I'm going to do is I'm going to take the limit of this nth partial sum, which is 1 plus a half plus a third, and then all this other stuff down here, plus 1 over n plus 1, plus, well, you know what? Did I forget to put minuses in there? Oh, I forgot to put minuses. Jeez, Robert. These were all minuses. I don't know why I didn't notice that earlier. Oops. Okay, so minus this, minus 1 over n plus 2, minus 1 over n plus 3. So let n go to infinity here. These all go away, and you're left with 1 plus a half plus a third. That's a common denominator there of 6. 6 over 6 plus 3 over 6 plus 2 over 6, which is 9, 11 over 6. 11 sixths. 11 sixths is the sum of that telescopic or collapsing series. I'll let you try 28 on your own. It's going to be collapsing. See if you can do that. All right, now the last sort of concept here in this section, which is kind of cool, I think. I hope I talk about this in class that I have time. The fact that when you look at the real numbers, if you write down a fraction, any fraction, doesn't matter what it is, you can always represent that fraction. So a over b. And here I'm saying a and b are integers, or elements of the integers, so that's coming out of the set. Like -3, -2, -1, 0, 1, 2, 3. As long as these are integers, you take any two integers and you divide them, then you're going to create what's called a rational number. All rational numbers can be represented as decimals, so this can be always converted as a decimal. But let me tell you something about this decimal. It either repeats itself forever, so it has like something where there's a pattern in there where it keeps repeating, or it terminates completely. So it's either like 1/4, which is 0.25, and then we say it terminates because there's really just 0, 0, 0, 0, 0. So we just say it terminates. Or if it goes forever, there's a pattern. 1/3 has the pattern 0.3333, so it repeats. Every fraction in the world is going to do either this or this. The numbers that do not do that are things like pi, and those will continue forever and never have a pattern. So if every fraction can be written as either a terminating or repeating decimal, then every repeating decimal or every terminating decimal should be able to be written as a fraction. And so that's what I'm about to do. I'm going to give us a repeating decimal, and we are going to have to write it as a fraction. And we'll use geometric series to do this. So we'll start out kind of easy, number 31. We're going to take 0.8888888 forever and write this as a fraction. So how do we write this as a fraction? Well, first thing I'm going to do is just write down what this is. This is equal to 0.8 plus 0.08 plus 0.008 plus 0.0008 and then forever, right? Because if I add these two together, I get 0.88. If I add them to this, 0.888, to this, 0.88888, and we keep doing that forever, we'll get all the 8s forever. Now this is equal to 8 tenths plus 8 100ths plus 8 1,000ths plus 8 10,000ths forever. But this is equal to 8 over 10 to the first power, 8 over 10 squared, 8 over 10 cubed, 8 over 10 to the fourth, and so on and so forth, which is equal to the sum as n equals 1 to infinity of 8 over 10 to the n. And this is a geometric series. What I'll do is I'll rewrite this. Since the 8 does not have the power on it, I'll put 8 out here, and then I'll put 1/10 to the n. And hopefully you agree that 1/10 to the n would just be a 10 to the n on the bottom. And so all I need to do to make this geometric is to rewrite this with an n minus 1 up here, since this is an n equals 1 to start. So what I'll do is I will find my hidden 0 in there. So we've got sum n equals 1 to infinity. We've got the 8 out here. We've got 1/10 to the n minus 1 times 1/10 to the first power. Now this is just a number, 1/10 times 8. So that's just 8 tenths, 8 over 10, which is 4/5. And then 1/10 to the n minus 1. And that is the perfect format that we need for geometric series. This is this is r, this is a. The absolute value of r is less than 1, so this should converge. It'll converge to a over 1 minus r, which is 4/5 over 9/10, which is 4/5 times 10/9, which is, let's see, that's a 2 there, so that's 8/9. If you take the number 8 and divide it by 9 on your calculator, you should get 0.88888 forever. That's the first example. It's pretty clean. Let me do 33, and that will probably help you do number 32 and 34 on your own. So number 33, if you have 2.516 repeated, so the bar there means that the 516 repeats. So this is really like 2.516, 516, 516. See, the 516 is the part that continues. And we need to figure out what that means. Well, how about this? Isn't this 2 plus 0.516 plus 0.000516 plus 0.000000516 plus keep going. So I get the first 516 here, then zeros there, 516. So if I put those two together, I'll get 0.516, and then when I put it together with this, I'll get 0.516, and then I keep doing that. The 2 out here is not really following the pattern. So I just peel it off, right? That's 2 plus this decimal. So I have 2 plus, now let me write these as fractions. Remember the place value, tenths, hundredths, thousandths. So 516 over 1,000 plus tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, millions So 516 over a million. And then 516 over 1, 1, 2, 3, 1, 2, 3, 1, 2, 3. So what do we got there? A billion, and we keep going. Now this is just 2 plus 516 over 10 to the third. Hey man, come on in. And then I'm finishing up. This is the last problem actually, so I'll be done here in just a second. This is the 8.2 homework for my face-to-face class, but if you do this, look at this, you'll be able to do the one online. Plus, let's see, 516 over 10 to the sixth, and then 516 10 to the ninth. Okay. The pattern keeps repeating itself out here. So this is equal to 2 plus sum. So I'm going to rewrite from here down as a summation. The 516 is always on top. And I have 10 to the, oh man, what are these? 3, 6, 9. The next one will be 12. These are multiples of 3, starting at 3. So I would put 3n here, n equals 1 to infinity. It's kind of small. 10 to the 3n. So let's check it. If I plug in 1, I get 3 here, so 10 to the third, 516 over 10 to the third. If I plug in 2, I get 6, 10 to the sixth, 516 on top. And it should work. Now that's a geometric series. The 2 is still out front. Okay, and then what do we want to do? Let's take the 516 here times, let's look at this as 1 over 10 to the 3n. So 1 to the 3n is still 1, 10 to the 3n is 10 to the 3n on the bottom. Now remember, I need to make this for geometric. If I'm going to start my index at 1, I need to make that an n minus 1. I don't like the 3 being there, so I'm going to write it this way. 516 times 1/10 cubed to the n. And that way I can get this from this. Now 1/10 cubed is 1/1000th. To the n. And all I need now is to make this an n minus 1. So I'm going to make it a minus 1, but then remember I have to multiply by 1 over 1,000 to the first power. So I kind of did that really quick. And I should be able to get this from this right here. I have, let's see, 516 over 1,000 is my A. I'll put it right here. 516 over 1,000 is my A. I have 1 over 1,000 to the n minus 1. So this is my R, this is my A. And so I should be able to use the formula for a convergent geometric series. So we've got here, notice the 2's just been coming along for the ride here. A is 516 over 1,000 over 1 minus 1 over 1,000. So 1 minus R, which is 2 plus 516 over 1,000 over, what's this, 999 over 1,000. And then I flip. So when I flip this, 1,000 here, 999, that's gone now. The thousands cancel, and I get 2 plus, let's see, 516 over 999. And finally, I need to put those two together. So I need a common denominator. So I multiply 2 times 999 on top, and on the bottom I have a 999. So 2 times 1,000 would be 2,000, but this is going to be 2 less, so it's going to be 1,998 over 999 plus 516 over 999. And I'm going to add those numerators up. So this is going to be 2,514 over 999. Yeah. Doesn't seem right. Hold on. I might have messed something up here. 2,514 divided by 999. No, I think that's it. What is this, 33? Oh, that reduces. It reduces, but this is fine. 3 goes in all of those. That's it. So that fraction, if you type it in your calculator, you should get 2.516516516516. Now I'm not going to do number 34, but I'm going to set it up because it's tricky. 34, they give you 10.135, but the 3.5 is the repeating part. So this is like 10.1353535. Okay, so the bar is only on the 3.5. So what I'll do is I'll rewrite this as 10 plus 0.1 plus 0.035 plus 0.00035. So notice that if I put these two together, I get 0.135. If I take that and add this, the first 3 decimals don't change, but then I have a 3.5 out there. I keep doing this. Plus 0.000035. And now I'm not going to touch these two. I'm only going to be looking at the part that's repeating. This is 10 plus a tenth. Common denominator there, 100 plus 1 over 10. That's 101 over 10. So that's this part. That'll carry with us the rest of the way. This part, you have to be careful. This is 35 over 10^100 thousandths, plus this is 35 over 10^100 thousandths, 10 thousandths, 100 thousandths. Did I get that right? Okay. And then the next one, 35 over 10, 1, 2, 3, 4, 5, 6, 7. So what you get here is 10 to the third on the bottom, 10 to the fifth, 10 to the seventh. And so when you do this, your formula is going to be a little different than the last one. Okay, you just have to create 3, 5, 7. You have to create the odd numbers starting with 3. So that's the important thing. You have to start with 3. So let's see how you do with that. It's kind of a challenging one. I'll tell you that the answer to that one should be 5,017 over, oh, well, you know what? Let me write it the way, not reduced. 10,034 over 990. And then you can reduce it. You can divide everything, reduce that out. Let me just double check it. 10,034 divided by 990. Yeah. That's what you should get when you do all of this work. All right. That is it for that section.